This module will be dealing with mainly the properties of the predictors, and also we shall be interested to derive the confidence interval of the predictor. It is understood that the forecasts are predictions, which has a future dimension as well as has a time series data. So based on that, in a regressive framework or in a two-variable regression model, we shall be understanding about the predictors, their properties, and also the confidence interval that is laid for the predictors. So in this context, we go for a regression model. In this regression model, we define a classical linear regression model by saying that yi equals to alpha plus beta xi plus ey, where I is running for the observations from 1 to n, and these observations are taken in a coordinate structure of y1, x1, y2, x2, and in this order. This is basically the equation where alpha and beta are unknown parameters and ui is the error term. So based on the least squares technique or OLS, we go by the estimated equation which comes up as y1 hat equals to alpha hat plus beta hat x1. So x1 is a particular value of x in the current period, and based on the x1, the y1 can be predicted. So x1 is independent variable. Putting the different values of the independent variable, the future values of y1 hat can be estimated or can be predicted. So this prediction is at par with the forecasting tool. Now we move on to the method of the prediction that will be applied. So first of all, we shall apply the method of point prediction, and when we shall be going for confidence interval, we shall go for interval prediction. So for point prediction, we mean the process of finding the value of the dependent variable from the estimated relationship for the known value of the independent variable not in the sample is called prediction. So what does it mean? It means that there is a dependent-independent variable relationship. Independent variables are taken in the sample, but when I want to find out the predicted value of the dependent variable, I take an independent variable outside the system. And this calls for the known value of the independent variable outside the system, and that is called the prediction or the predicted value. So this also says that x0 is the value of the independent variable, for example, for which we want to find out the predicted value of y, which can be said to be y0. So basically when we look for the point prediction, then we deal with the variable wise that for a particular value of x, that is x0, we want to find out the predicted value of y as y0, and thereby the prediction technique can be applied. This entire method comes under the notion of point prediction. Now when we go to the point prediction, we basically look at the single value because it is done on that way. So when the prediction is done in terms of the single value of the dependent variable, it is called the point prediction. So simply what we say that we have the equation which is y hat equals to alpha hat plus beta hat x. So in place of x we put x0 because given the value of x0 we want to find out the predicted value of y, which is considered to be y hat, and this has a name called y0. So y0 is basically a single observation which is a predicted observation based on the independent value of x when x takes x0. And that is actually done under the point prediction method. Secondly, we can see that now y0 is the true value of the dependent variable y when prediction is made, and it is given by in this way. So particularly we can see that y0 is basically equals to alpha plus bx0 plus u0, because again this y0 will follow a relationship with x0 and it can be considered as a linear relationship where y0 is the disturbance term of the term, because this disturbance term is the u0 which takes up. So actually what we observe in this particular slide is this, that y0 is basically a specific value or the forecasted value of y when we write x as x0. Now we want to find out the mean of this y0, and we know that this y0 follows again a random series. So y0 is treated as a random variable because it depends upon the chance of occurrence, and accordingly we need to find out the expectation of a random variable. So this expectation says that expectation of y0 equals to beta expectation of alpha plus x0 plus expectation of u0. Why? Because we are basically using this in this equation, and from there we are getting the name of alpha plus b x0. So in all this derivation we observe that x0 is an unbiased estimator of x, and we know that on average the sum of the errors is 0. So expectation of u0 is 0. So based on that, expectation of y0 is being made out. So based on this, we go for the method of point prediction. So when we are looking at the point prediction, we mean that error is the difference between the actual value of the y0 and the predicted value of the y0. And thereby when we find out the error e0, we can go for y0 as a random variable, which is the actual value. So we insert expectation of y0 minus y0 as the actual variable. So here we observe in this particular slide that this e0, which is the error term, is expectation of capital Y0, because Y0 is defined as the random variable, minus this Y0, which is basically the predicted value of the Y0, and thereby we want to predict EY0. So this EY0 plays an important role because this Y0 follows a random variable and it is actually based on the chance of occurrence. And thereby we are interested to find out the mean of this y0, which is the predicted value, and also the variance of this y0. So this motivates to go for the mean of the predictor, which is y0, as well as the variance of the predictor, which is also the variance of y0. Now we go for the derivation of the mean of the predictor, that is y0. So when we want to predict y0, first of all we need to look at the expression of error, which is e0. So we observe e0 is equal to y0 minus y0 hat, that is the step 1. So in the step 1 we observe that error is the difference between the actual value of y0 minus the predicted value of the y0. Now, in that way, we are substituting the expression of y0 in this expression, which is alpha plus beta x0 plus u0, because that is how the expression of y0 comes in. Minus, we go for y0 hat, which is the estimated value of the intercept, which is alpha hat, and then we have beta hat x0. So alpha hat and beta hat x0 are considered as the estimated values of alphas and betas. And then we have the y0 as the equation. So after simplification, we go for the step 3. So in the step 3, we observe e0 is equal to u0, which is considered as the error, minus within bracket alpha minus alpha hat. Alpha is the actual value of the population intercept, minus alpha hat is the estimated value of the intercept. In the similar fashion, it is written minus within bracket beta minus beta hat, which is the slope coefficient actually and the estimated, bracket closed, multiplied by x0. So this particular expression is the expression of the error after expanding the expressions for y0 and y0 hat. This is how the step 3 comes in. Now as we proceed for the next slide, we observe that the step 3 is again repeated here, which is u0 minus within first bracket alpha minus alpha hat, bracket close, minus within first bracket beta minus beta hat, bracket close, x0. So this is the step 3. Now we have already said that this e0 is always a random variable. So in order to find out the mean of the e0, we need to find out the expectation of e0. So we insert expectation of e0 and we put expectation beside all the random variables which are taken up. For example, expectation of e0 is equal to expectation of u0 minus expectation of these constant terms. Then we have expectation of this difference between the actual and the predicted value of the slope coefficient into x0, which comes up as the specific value of x equals to 0. Why 0? Because according to our OLS assumption, the sum of the errors must be 0. So thereby the expected error or expectation of e0 is 0, which is step number 4. So we know expectation of u0 is equal to 0 and alpha hat equals to alpha means the alpha hat is an unbiased estimator of alpha. Similarly, beta hat is an unbiased estimator of beta. So putting everything here, we are actually ending up at expectation of E0 is equal to 0. So again, using the same kind of E0 or using the expression of the predictive model, we can even prove that on average the sum total of errors is 0, which is actually the normal assumption under the OLS. So now if we go for the final expression of y0, then we can see y0 minus expectation of y0, because by removing this bracket from step 5, we can put y0 outside the expectation because it's a specific value that we have computed. It's not a probabilistic value, it's a specific value, minus expectation of y0, which has already been coming up, is equal to 0. So by rearranging the terms, we get our final result, which says that y0 is basically an unbiased estimator of y0 hat. So whenever we consider y0 hat as the predicted value of the y0, we can see that y0 is an unbiased estimator of y0 hat, and so this goes for saying that any kind of OLS property regarding the unbiasedness property is easily solved in this manner. So y0 is the OLS point predictor of y0, and that is unbiased. So we can see that y0 hat is an unbiased estimator of y0, and thereby we can say that this is also following the blue property as it is done under alpha hat and beta hat. So in order to find out the mean of the predictor, which we have done, we have considered the step 4 once again to find out expectation of E0, which is equal to 0, and this is already being done in the step 5. Now we are writing step number 6 again. Why? Because this E0 is again written in step number 6. Putting the expectation again, we go back to the final result of step number 7, where we observe that on average expectation of E0 is 0. So by rearranging the terms, we can see y0 hat is the OLS point predictor of y0, and it is unbiased. That means y0 hat, which is being computed, is a point predictor of y0. So y0 is basically the population parameter, and based on that the y0 hat comes up, and that is how the step 8 comes up. So regarding the mean of the predictor, we can see that y0 hat is an unbiased estimator of y0, and thereby the OLS or the point predictor of y0 is being computed. This actually motivates to look into the variance of the predictor, whether the variance is minimum or not. Then only we can look at the efficiency of this predictor, or we can go in tune with the best linear unbiasedness estimator. So for the variance, we apply the formula of expectation of y0 hat minus expectation of y0 hat whole square. This is the step 1. As by the expression of variance of x, and if x happens to be a random variable. Based on that, we have just now seen that y0 is an unbiased estimator of y0 hat. So in place of y0 hat, we can write y0, and thereby we can go for equation number 2 because it is unbiased estimator. Now this difference is actually the minus of the error E0. But since it's in the square form, the minus is getting eliminated, and we get expectation of E0 square as the final expression of step number 4. So in this particular slide, we can see that variance of y0 hat boils down to expectation of E0 whole square. Now as we go to the next slide, we repeat the expression of expectation of E0 whole square, and we go to step number 5 from step number 4. So in place of E0, we write down the entire expression again, which is already shown here, as we say that we know that E0 is nothing but U0 minus alpha hat minus alpha within the first bracket, then minus beta hat minus beta within the first bracket into x0. So we put the entire expression in equation number 5. Now this equation number 5 is repeated in this slide just for the continuity, and we actually expand the terms. So after the expanding terms, we get the square terms and we get the cross terms. So when we are looking in this particular slide, we start with expectation of E0 square. This is equal to expectation of this expression, which is in square form. So that's equation number 5, which is repeated from the last slide. And then we come to the equation number 6. This equation number 6 is squaring off each of the individual elements of step 5. That is expectation outside the bracket, and we have u0 square as usual plus alpha hat minus alpha whole square minus beta hat minus beta whole square x0 square, as if we are doing a minus b minus c whole square. So each of the items are treated separately in the square form. And then we have the cross terms like minus 2, which comes up as alpha hat minus alpha u0. That is the first cross term we consider. The second cross term is minus 2 beta hat minus beta x0 u0 by multiplication. And the remaining cross term is plus 2 alpha hat minus alpha beta hat minus beta x0. So the 2 comes up because these are the cross terms which are considered, and that comes out to be step number 6. And after that, we are basically removing the bracket and inserting expectation before every item. So we insert expectation before u0 square. We insert expectation before alpha hat minus alpha whole square. Similarly, beta hat minus beta whole square x0 square. And by doing this, we insert expectation beside all these combinations or these values. And that comes up to be the equation number 7. So the first one is nothing but sigma square u, which is basically the variance of the error term. Next we have alpha hat minus alpha whole square is nothing but the variance of the intercept, that is the estimated intercept alpha hat. Next we have variance of beta hat. Then we have two covariance of alpha hat u0. This is basically very important because it is a cross term which shows the association between the estimated intercept and the error. Similarly, covariance terms are given on the respective associations between the beta hat and the error and among the respective coefficients of intercept and the slope. So these are the cross terms. So after inserting the entire thing in the variance of the predictor, we observe that by the OLS estimator's assumption, all these u or alphas and betas, whatever we have in the model, they are non-stochastic, because they are not related with the error term. This is one of the basic OLS assumption. So by putting the covariance equals to 0, we are left with only the covariance of alpha hat, beta hat, which will exist, but the other covariance terms will become 0. So that is what we do in this particular slide. We put all other covariance terms are 0 because there is no relationship between the independent variable and the error term. But we have the covariance of alpha hat and beta hat, and thereby by putting the respective expressions, we get equation number 9. From equation 9, we slowly go to equation number 10, which is written in terms of mean value. And finally, we can end up with this expression minus x bar variance of beta. So whenever we are expressing this covariance between alpha hat and beta hat, it is basically expressed as minus of x bar, that is the mean of the x, into variance of beta, which is the variance of the slope coefficient. That is the equation number 12. So based on the equation number 12, we can now go for the final expression of variance of y0 hat, which is again repeated here, and we go by equation number 13. From 13, we put this entire expression, which is written as equation number 14, and finally we get the variance as sigma square u plus variance of alpha plus x0 minus x bar whole square into variance of beta minus x bar square variance of beta. So that is basically the final step of equation number 16. So by equation number 16 in the next slide, what we can see that if the variance of beta is minimum, then only we can see the variance of y0 hat will be minimum. So we can observe that this is basically the blue property of the OLS point predictor, that variance of y0 hat will be minimum provided variance of beta is minimum and also it is unbiased. So based on these two properties, we can see that the OLS point predictor is satisfying the best linear unbiasedness property. After the discussions of the OLS properties of these predictors, which happens to be unbiased and having the minimum variance, it is crucial to look at the confidence interval of this predictor. So for the confidence interval of the predictor, we need to reject or accept the hypothesis testing, which mainly goes by the null and the alternative hypothesis. So in this particular slide, we shall be discussing about how the confidence interval for a predictor can be done, which is based on the interval prediction. For example, we start with the very first hypothesis that suppose H0 or H0, which is the null hypothesis, says expectation of Y0 equals to A. So this A is a specified value of the observation. Expectation of Y0 is the mean and Y0 is a random variable. So it is said that the mean of this Y0, which is a predictor, is equal to a specific value which is capital A, and accordingly we can go for the two tests of the distribution. That means it can be at both tails, right hand and the left hand tail of the distribution. So we go for HA, which says that expectation of Y0 is not equal to A. So based on this hypothesis, we can see that when we can accept the null hypothesis or when we can reject the null hypothesis. So this calls for saying that Hn will be accepted. That means null hypothesis will be accepted if the computed value of the t lies within the left tail and the right tail of the distribution. Since we are mentioning not equal to A, we consider the level of significance to be alpha by 2. So this goes by a t distribution where the underlying distribution is normal because all the OLS assumptions are satisfied by these OLS estimators or the predictor estimators. So we get the lower range or the lower limit is t, the table value is 0.025 comma n minus 2, which means it is at alpha by 2 where alpha is 0.05 and n minus 2 is the degrees of freedom because we are dealing with a two variable regression model. Now we have the observed value of the t. This observed value of the t is basically the computed value, and then we have the upper range which is 0.025 comma n minus 2, and thereby we want to see whether the observed value of the t lies between these two ranges. Now we go for the one-tail test. So by one-tail test we mean either we go for the greater than sign or the less than sign. So this goes to the next important alternative hypothesis where we want to claim that the mean value of Y0, that is expectation of Y0, is exceeding the specific value. So the null hypothesis is the same where expectation of Y0 equals to A, but the alternative hypothesis says greater than A. So based on that, we can see that Hn will be accepted if the observed value of t is less than this. That means if the computed value of the t is less than the table value and it lies on the left tail of the distribution, then definitely we are accepting the null hypothesis and we are in the rejection region of the alternative hypothesis. Similarly, if we refer to the alternative hypothesis of EY0 less than A, less than A means we look at the less than equal to sign. That means since the alternative hypothesis of the less than type, so rejection of the null occurs if the computed value of t is greater than equal to t 0.05 comma n minus 2. So here the attention to be given regarding the nature of the inequality that we are taking in the alternative hypothesis. So in the first case it was greater than A, and in the second case it is less than A. So when it is greater than A, then we go by the decision rule where the observed value is less than equal to the table value, and when it is less than A, then the observed value is greater than the table value. So based on all this, we can set up the 100 1 minus alpha % confidence interval, and we can see that the predicted value of Y0 hat will be plus minus t, where we go by the both tail or the two tail test and we write the variance of Y0 hat as it is. So alpha can be 0.05 or can be 0.01. So now we finally come up to the summing up of this particular module 20. So in this particular module 20, we have actually derived the OLS properties of the predictors, which is Y0, and we have used the point prediction method. And by applying the point prediction method, we have seen that the predictor always satisfies the OLS property, that is, it has the minimum variance and it is unbiased. Secondly, the derivation of the properties are being done based on the derivation process that we followed in the normal OLS method. And then we are interested to find out the confidence interval of the predictor that goes with the hypothesis testing. That means whether we go for a one-tailed test or a two-tailed test, we reject the null hypothesis if the computed value of the t is exceeding the table value or depending upon the sign of the alternative hypothesis. So finally in this module, the predictor properties and the confidence interval are greatly elaborated.